Really, I could go on, but there isn't any point because he needs the time to do his keynote. So I'd like to bring up Zig Engelmann, and there you go.
Wow, what a group. Okay, well, you're in luck because today we're going to be talking about theory of instruction. If I just find the right button here. Oh, I got it. And the theory of instruction is important primarily for legitimacy. Like, DI is not legitimate. It just is talking out loud. It is rote learning. It's talking down to learners. It doesn't take into account Piaget's theory or other developmental theories. And it has no substance, basically. And they downplay the fact that DI works. For instance, like there are a lot of studies on DI. One recently came out and it compared decoding skills in Florida of lots of kids. And DI came out the highest, and they entered the lowest. And begrudgingly, this article acknowledged that. But it was begrudging because it didn't come out and show the data as it were. It was twisted so it looked like the gains and the differences between DI and the other comparison programs and were small. They weren't small. From the lowest to DI was probably half a standard deviation, which is a significant amount, a big effect. So, wow. Okay. I love technology. Anyhow, so for legitimacy purposes, DI theory is important. And I know how much you love theory. And for this one, we're going to have to go back to the 1600s where we start. Heck of a deal. Heck of a year. And we want to show that DI theory is an extension of a very reputable philosophical strand called empiricism. And here they are. The fundamental assumption of all empiricists is all knowledge comes from experience. And this is a natural link with education. Unfortunately, none of the philosophers on that list used educational examples. The guy at the bottom of the list, John Stuart Mill, came the closest, and he even pointed out that his system of induction could be used and should be used in education. But he didn't give any educational examples, only science examples. But the link is natural because the assumption is the assumption of education. If all knowledge comes from experience, and we want kids to have particular knowledge, what are we going to do? Control the experience so that it comes out. And they should be concerned with the details, the logical details of how that comes about. Anyhow, it all began with John Locke, an essay concerning human understanding. And his notion was that the kid comes into the world with a tabula rasa in his head, a blank slate. And that experience writes on that slate, and that's all that happens, and it comes through sensation. All right, so a few years later in 1710, George Berkeley wrote a treatise concerning the principles of human knowledge, and in that he disputed or modified some of Locke's principles. That what he said basically was like this. True, you have two sources of knowledge. You have knowledge of yourself, and you have knowledge that comes through experience. But what happens when you're not there to experience something? Well, he postulated that God was there. And so the conundrum about, the tree falling in the forest doesn't make a sound if nobody's there. Whoa, somebody's there, not to worry. Even if you're not present. Okay, so there's a natural link, and we're getting farther away from that natural link. David Hume took great issue with Berkeley, and he wrote an inquiry concerning human understanding, and it was based on pure skepticism. I mean, he did not have a lot of regard for Berkeley or his theory, and his position was pretty well summed up in the last paragraph of the inquiry. And this is interesting because people were beheaded at this time for saying things not as seditious as that, what Hume said. What did he say? When we run over our libraries persuaded of these principles, what havoc must we make? If we take in our hand any volume of divinity or school metaphysics, for instance, let us ask, does it contain any abstract reasoning concerning quantity or number? No. Does it contain any experimental reasoning concerning matter of fact and existence? No. Commit it then to the flames, for it can contain nothing but sophistry and illusion. That what Hume thought happened was sensation comes in, registers in the brain, and that's it. And that you, as a person, use all that information deductively. In other words, you want to think of a blue dragon. Huh, okay. Well, you got blue over here, you got dragon over here, they're both in your mind. Bang them together, and what do you got? A blue dragon. Hell of a deal. I mean, they just don't make them like that anymore. And there was one problem. He had no basis in his theory for how somebody could learn from examples, to derive a rule from examples. That's called induction. All he had was kind of top-down reasoning. And he acknowledged in the footnote of one of the things he wrote that I have no doubt that somebody could identify blue, a shade of blue they had never seen before. But then he added, this is a singular and unimportant example. Wrong, because along came John Stuart Mill a bit later and tore up the road. His whole system was based on induction. His system was based on the idea that you could use examples that were consistent with a rule and induce the rule. Whoa. Okay, so we're going to go over Mill's principles because they're very close to the ones that are used in direct instruction. The wording is a little better than we used in theory of instruction, but I'll read and translate. If two or more instances of the phenomenon under investigation have only one circumstance in common, only one little part of them is the same, the rest is different, only one part is the same, you got a bunch of them, the circumstance in which alone all instances agree is the cause or the effect of a given phenomenon. Let's go back to blue. All right? So one circumstance that's the same. Let's make them all the same in blue. Everything else different. So we'll assemble a set of examples. Let's see, different. A blue sky, a blue lake, a blue table, a blue wall, and two blue balls. Okay, there we have it. Like they're the same in one circumstance. What circumstance? Blue. Everything else is pretty different. A blue sky is kind of amorphous. A blue lake has a shape, but nothing like a table or a ball or anything like that. So that, now here's how it goes. The causes come from what the teacher said. And the idea is, this is an instructional analogy. The assumption is that something caused the teacher to say these things. What was it? So the teacher points to each one of these and says, this is blue, this is blue, this is blue, this is blue, and these are blue. Wow, what caused the teacher to say that? There is only one possible circumstance that caused the teacher to say it, and that's the blueness. And that's what the assumption is, the logical assumption of what one would learn. Okay, method of difference. He has 5 of these methods, so we're making progress. If an instance in which phenomenon under investigation occurs and an instance in which it does not occur have every circumstance in common save one, the circumstance in which alone the 2 instances differ is the effect or the cause or an indispensable part of the cause of the phenomenon. Whoa! Well, here it says they differ in only one circumstance. The others were the same in only one circumstance. These differ in only one circumstance. So let's put it together. What do we got? We got a blue bird here, okay? Blue. And we have another bird that's identical in every respect except for blueness. And now what causes the teacher to say, this is blue, this is not blue? There's only one possible thing that could do it, and that's blue. Blue moon. Okay. Okay, does that make sense? No? Well, the others won't either. The next is a joint method of agreement and difference. And this presentation is the only one that's really consistent with one possible inference. You can only draw one possible inference from this. With the first one, you see blue, 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 blue. That shows what blue is, but it doesn't show where it ends. So what's to prevent me from going through that and seeing something purple and say that's blue? Nothing. But when we put these differences on the end of it, so now we got a bunch of blue, 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 and we got critical, minimally different examples, not blue, not blue. Bang! It gives you a schema, a gestalt, a map, or whatever you want to call it. But you draw the correct inference. Okay, finally, second from finally, this one's hard to understand. Deduct from any phenomenon such part as is known by previous inductions to be the effect of certain antecedents, certain causes, and the residue of the phenomenon, that which is left, is the effect of the remaining antecedents. Well, here, let's construct an educational example. Here, the phenomenon is a pattern that involves a whole bunch of examples. Some are more difficult, some are less difficult. And the kid knows some of these through past previous inductions. He's learned some of the easier examples. He doesn't know the harder ones. So what do? You set it up so it's clear that the residue, or what he learned about the pattern from those few examples that he knows, applies to all the rest of them. Bing, 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 bing. Oh, whoa. Now this is not like blue, because it's not yes, no, it's not either this or that, it's a pattern. So, like, what kind of example could we come up with here? Think of this. Here's a kid, and he can do this. Listen. Motor boat. Say it. Motor. Say it fast. Motor. Ice cream. Say it. Ice cream. Say it fast. Ice cream. But here's what he can't do. He's looking at this word and he says, and the teacher says, say it fast. And he can't do it. Whoa! So that's a description of this. So we take the pattern he knows and we sequence it so that we get to the stuff he doesn't know, and we make sure that he understands it's just an example of the same damn pattern. And somewhere along the line, as we're sequencing these, we'll put in some examples like this. Listen, and say it fast. And that's what they call now phonemic awareness. No, Virginia, it's the method of the residue. And if it's done properly for reading, you're just applying the pattern that he needs for reading. And if you have to do the one for spelling, you do the one for spelling. Listen and say it apart at a time or whatever. But you would have a similar series, because the learner would probably be able to do some of them, but not others. Okay, last of the methods, here we go. Whatever phenomenon varies in any manner, whenever another phenomenon varies in some particular manner, is either a cause or an effect of that phenomenon, or is connected with it through some fact of causation. That's another. Okay, translation. Let's go to the fact of causation. Let me think. Okay, hotter air rises. Okay, hotter air rises. And those are things that concomitantly vary, right? So let's do it. I'll tell you about the temperature of the air. You tell me whether or not it rises. Here we go. The air starts out at 65 degrees. It ends up at 65 degrees. Did the air rise? How do you know? It didn't get hotter. Okay, listen, the air starts out at 65 degrees, goes up to 81 degrees. Did the air rise? Yes. How do you know? It got hotter. Well, what is that? That's the method of concomitant variations. Woo, this is getting heavier. Okay, so those are the 5 principles. There were problems with some of Mill's science applications because he's been criticized for that you have to know the causes to apply the methods. Well, this problem is totally obliterated if you use it in instruction, and here Mill was. He used examples, like commonplace examples in his introductions and his discussions, but he didn't use them as they related to his theory. But he knew this stuff. He understood it. He stood on the doorstep of being able to change the damn world by introducing logic in education so that people would have a sensible and theoretical basis for designing effective instruction for kids. It never happened. But these problems disappear. All the problems that have been noted about Mill's methods and how they're incomplete and so forth don't apply to instruction, because when we apply them to instruction, we design them so they are consistent with only one possible inference. And if there's a question about whether we have done one circumstance difference or more than one, why, we'll figure it out. And if we don't figure it out when we try it out with kids, they'll let us know. Okay. And the basic assumption of all of this is if learners are firm on the examples, they can correctly respond to all the examples, they will learn the correct inference. Okay, let's fast forward ahead to these dudes. Engelmann and Carnine, Theory of Instruction in 1982. That's 10 years after they started working on this program. They worked on it during most of that period, an hour and a half a day. And for 9 years that went on. It involved like many revisions, and it had no knowledge of Mill's principles. We didn't find out about Mill's principles until we had finished writing the bulk of the work and we were doing a chapter on theoretical issues. And when I first read Mill's principles, I said, oh, I talk like this to myself sometimes. Holy crap! I mean, because, ta-da, this is from Theory of Instruction, to show sameness across examples, juxtapose examples, put them one right after the other, that are greatly different, have only one circumstance in common, and indicate that the examples have the same level or label or treat them in the same way. This is Mill's method of agreement. I mean, we figured it out the hard way. We could have read the damn Mill thing and saved ourselves a ton of time. Okay, to show differences, juxtapose examples that are minimally different and treat examples differently. Minimally different means they differ in only one friggin' circumstance. And So this is Mill's method of the difference. And we have transformations, which is Mill's method of residue, and we have correlated feature sequences, that's what we call them, extensive, that are Mill's method of concomitant variation. And we also have sequences that show that joint union of the agreement principle or method of agreement and method of difference. So that basically we had educational counterparts for everything he had. Our theory went a lot farther because it dealt with teaching, and the logical analysis tells you some things about teaching, tells you how to design the set of examples. It doesn't tell you much or anything about how much practice it's going to require for kids to learn this stuff. So that's empirical, and there are sources of empirical evidence about behavior, so that it combined the analysis of behavior with this analysis of logic, and then it had to be combined with the third one, which is knowledge of the subject that you're teaching. If you don't know it pretty well, you can't take it apart and simplify it or do things that are efficient with it. Anyhow, we had everything that Mill had, and we had a bit more, but the core of it was Mill's stuff. And then, as part of this, we did, I should say Doug Carnine did, empirical investigations. It would work like this. We'd be writing along and we'd draw a conclusion that was based on the logical evidence of the theory so far. And Doug would say, do you know of any studies that confirm that or address that? And I'd say no. And I'd say, do you? And he'd say no. And he'd make a little note, and then we'd go on. And a month or two later, sometimes as long as 4 months later, he would have conducted a field experiment with experimental group, control group, all the methods, the procedures, so that this work could be published in a professional journal. So the logic analysis was validated. It was validated. Virtually all the studies confirmed the logical prediction. There was only one exception, major one, and that was that we predicted that if you started a sequence with the negative examples first, like this is not Glurm, this is not Glurm, and then you show them what Glurm is, this is Glurm, and you show all the samenesses there. Okay, that they would learn it faster than if you started with the positive example. This is Glurm, this is Glurm, this is not Glurm, like that. And that was based on just logical considerations. So Doug tried it out with two groups. One was a preschool group, and another was law students. And for the law students, they had a different example than the preschool group. And it was confirmed with the law students, but with the younger kids, it was disconfirmed. So we checked the kids out to see what was happening. And it turned out that when you said, this is not Glurm, they were thinking like this, okay, so I'm not interested in it. When you have something interesting to tell me, let me know, And then when you said, this is Glurm, oh yeah, but you didn't pay any attention to the negative examples. But aside from that, all of the predictions that we made that were unique were validated by one or more studies. So the logical analysis was validated through so many empirical investigations. How many? How many do you think Doug did during that period? Give me a number. Do I hear 12? Do I hear more than 12? Raise your hand if you think it's more than 12. Okay. Raise your hand if you think it's more than 20. Okay, more hands are going up. I'm not giving the answer. Yeah, it's more than 20. Raise your hand if you think it's more than 30. Okay, raise your hand if you think it's more than 40. I'm almost giving it away. Okay, raise your hand if you think it's more than 50. No, it's not more than 47. 47 published studies for theory of instruction. And yet if you look it up on the internet or something, you won't even see it listed as a theory of instruction. You'll see some Mickey Mouse about Piaget and equilibration and accommodation or some other such abstractions that are irrelevant. So the ultimate test of DI programs developed by these principles, we always, just as we did with the book, to check out to make sure we were not merchandising something that is less than true, that we always field test them. And the reason is, although we can apply these logical principles, we can't determine how much practice it's going to take. So the only way we're going to figure that out, and the only way we're going to figure out where we screwed up, is through field testing. And I mean, you know, we will screw up. We'll do the best we can at judging this stuff, but when you're teaching a whole body of things together, you can do things that you think will work, and sometimes they don't. So we always field test them, and that's the bottom line. That if it doesn't come out as we anticipated, we're not going to bitch and moan about it. We will take the data and we'll try to fix the program up so we obviate that problem. Okay, and now, so here, you want to know about the learner's mind? You want to know what's relevant about the learner as a learner? Here's the ultimate argument, and I've given all the data for this argument. The principles of inferences are logical. Is that right? Yes. Experimental evidence, those studies, confirms that learners draw the inferences that are based on these logical principles. 47 studies worth. Therefore, the learner's mind performs the logical operations. That doesn't mean that they perform the logical operations like as a product of cerebration. Here's an example, okay? Mother's driving with her kid along on a highway, and all of a sudden, the kid, 3-year-old, he points out the window and he says, "Mommy, big car." And she looks and she says, "No, honey, that's not a big car, that's a truck." But, okay, a couple of things indicate that learner's mind was totally logical, but it wasn't presented to the learner as the product of information that the learner had. In other words, it wasn't part of her consciousness at all. She just looked at it. It wasn't like this. A vehicle, let's see. Could it be a bicycle? No, it has too many wheels. Could it be a boat? It's moving, yes, but it doesn't have a lot of well, looky, it has windows, doors, an engine, wheels on the ground, makes that big noise, and goes down the roads. And it's a car. Okay, but it didn't happen like that. It happened in a heartbeat, in an instant. The kid looked at it, and the epiphany hit the kid right in the face. Big car. Hot damn. And so don't confuse the fact that it's logical and necessarily logical with the fact that it's not conscious. You don't do that. You're born with that. And Piaget and all these other guys with, really infractious systems of verbiage and how development interfaces with learning, wrong. Knowledge is knowledge. It doesn't matter whether it's a high performer or a low performer. They'll all perform the same damn inferences. And if you present the information so it's consistent with a single inference, they will tend to learn it. So that's the ultimate argument, almost. Let's see what yeah, that's it. The mind is perfectly logical. And see, you can get those jump up and down epiphanies, and you can prove to the kid that she's a competent learner by controlling the presentations, the inferences, the amount of practices they receive, and you can give them information I was able to do what the teacher said. I was able to do what the teacher presented. I was able to do that. I'm pretty damn smart. And that is what it's all about. Have a great conference. Thank you very much.